So this is the image diagram for an astronomical telescope. So first we will do when the final image is at infinity, which is called the normal adjustment. So this is the principal axis. This is our objective lens. Now rays of light that come to the objective lens, so are parallel to each other, and let's say the one of the ray is traveling through the optical center. This is another ray. Now this ray will get focused, and this ray is, let's say, another of our parallel ray, and this ray will also get focused here. So all of them get focused here to produce an intermediate image which will lie at the focal plane of the objective. So that means this is the focus of the objective, and this is where an intermediate real image of height h is formed. So this is alpha. Why is it alpha? Because the eye is maybe somewhere here, but the length of the telescope is insignificant compared to the distance of the object from both the telescope and the eye. So the angle which the rays of light subtend at the telescope can be taken as the angle subtended at the eye, and therefore we have our alpha. Now the second lens is placed. So say this is our second lens. Now the second lens is placed like this, in such that the focal length of the eyepiece, that is our second convex lens, coincides with the focal length of the objective, so that the final image, so let's draw this in blue, the final image will be formed at infinity. So this ray of light, say, is parallel to the principal axis. So these rays of light, so the ray of light that is here, so this is the focus. So this one, so if this happens to be parallel to the principal axis, this will also go to infinity. So all these rays of light will meet at infinity. So this is how the ray diagram is done. If you want to find the path of these other rays, you could do the same thing. Like for example, this one will also be parallel. So just be careful, and these are the rays. So our beta is here, and this one, mind you, is, so from here to here is FO, and from here to here is FE. So magnification is beta by alpha. Alpha is h by FO, beta is h by FE. Therefore magnification is FO by FE. So this is for the final image at infinity. Now let's do the second one. The next one is for the final image at the normal adjustment, or rather the final image at the near point. So this is once again our principal axis, and then we draw the objective. The first part of the diagram is the same. So we have got rays of light that come from infinity and are parallel to each other. So let's say they get also focused at the the focal plane of the objective. So this is how it is done. So they form your inverted real image here. So this is the focus of your objective, and this distance is the focal length of the objective. Now the second lens, which is the eyepiece, is placed here such that this one, say, is a ray of light parallel to the, so the second lens is placed in such a way that parallel to the principal axis. So let's say it passes through the focus. So ray of light that passes through the optical center, which goes without any deviation, and the ray of light traveling parallel to the principal axis will pass through the focus. So we can put our focus as being here, say, so that the final image is formed here. So this, in that case, is the focus of your eyepiece, which means if I were to measure out the same distance, which is say 1.8, in that case it will be somewhere here. So your FE is here. That means in the previous instance, the focal length of the objective and the focal length of the eyepiece, they were coinciding, that is, they were at the same point. But in this case, the intermediate image which you see here is formed within the focus of the eyepiece, so that the final image is formed where it is formed here at the near point. So in our diagram, our near point comes here. So this distance is D. Now this is alpha, this is beta, and this one is UE. That means the object distance for the eyepiece, and this is H. So if you look at this, alpha is H by FO and beta is H by UE. So magnification is beta by alpha, which is going to be FO by UE. You can leave it here, but we can do further. Applying the lens equation to the eyepiece, I have 1 upon F is 1 upon, now V is D with a negative sign, because this is our image, and this is the image distance. So this is minus D and plus 1 by UE. Okay, so we'll just is minus 1 by minus UE. Why? Because the object distance here is to be measured. This object distance is to be measured again to the left. So it comes out negative. Now this one becomes 1 upon F plus 1 by D is 1 by UE, and this is 1 by UE that we want here. So beta is or rather this one, this 1 by E is what we have here. So magnification is FO, and instead of 1 by E, I can write 1 upon FE plus 1 by D. Mind you, this is the focal length of the eyepiece, because we were applying the lens equation for the eyepiece. So this one is FO D plus FE DFE. So I can take my FE out and I get D plus FE by D. So we have got two expressions for magnification: FO by FE at normal adjustment, and M is FO by FE D plus FE by D at near point, when the final